Hi, my name is Ray, and I'll be talking about the zero rate threshold for adversarial bit deletions is less than 1/2. This is joint work with Venkat and Xiaoyu. So our main result is both a coding theory result and a combinatorics result. So I'll give you the combinatorics result first and then the coding theory interpretation. So first, a warm up. So we let the LCS of two strings denote the length of their longest common subsequence. Here are two strings with 0, 1, 1 as a subsequence, so their LCS is 3. Notice in the second string, 0, 1, 1 does not appear consecutively, so subsequences are not necessarily contiguous. For a set of strings C, we let the LCS of C denote the maximum LCS between two distinct strings in the set. And the warm-up question is, what is the largest set of binary strings we can find with LCS less than n over 2? So the LCS between any two is less than n over 2. So I encourage you to pause the video, think about the warm-up, and then I'll show you the answer. The answer is 2, and you can find a set of two strings with LCS less than n over 2, and in fact, LCS 0, you take the all 0 string and the all 1 string. And what happens if you have three strings? Then there's two strings with, say, at least as many 1s as 0s, and then they have the all 1 string as a length n over 2 common subsequence. So that was the warm-up. Now, what happens if we replace 0.5 with 0.5 plus delta for some very small positive constant delta? Now, in this relaxation, you could potentially find a larger set of strings, but it turns out this question is much more difficult. In fact, we had very bad bounds, a double exponential gap between the best lower and upper bounds. The lower bound, there was a construction of log n strings with pairwise small, less than n over 2 plus delta n LCS, and the best upper bound qualitatively was not better than the trivial bound. That is just an exponential bound. So there's this double exponential gap, and what our result shows is that we improve the upper bound to quasi-polynomial in n. So it's an exponential type improvement. To be super precise about the quantifiers, we show that in every set of binary strings of a sufficiently large quasi-polynomial size, there exist two strings with LCS n over 2 plus delta n for some absolute delta. So that's our main result. It's a combinatorics result, which I indicate with a Rubik's Cube. So that was the combinatorics result. Now I'll give you the coding theory interpretation. So coding theory studies error-correcting codes, which for our purposes are simply sets of strings. We'll be studying binary codes, so sets of binary strings, and these strings typically have the same lengths, which we denote n, and we call this n the length of the code. The setup you should imagine is that a sender, Alice, wants to send a message to a receiver, Bob, but there's a noisy channel in between, so Alice encodes her message in the error-correcting code with enough redundancy that Bob can recover the original message, even in the presence of errors. So in this protocol, you should think of the code as the set of strings Alice sends, and we call the elements of our code words, so Alice sends a code word. And the success of this protocol depends on the mathematical properties of the code. So what properties would we want? Well, one thing we want is we want the code to have large rate. The rate, denoted R, is defined as log of the size of the set divided by n. So you can check it's always the number between 0 and 1. And another way to write it is the size of our code is 2 to the R times n. So an intuitive way to think about the rate is it's the length of the message that Alice sends, that Alice encodes, is R times n. So the code here has size 4, so you can calculate the rate is log of 4 over 6, which is 1/3. But a more intuitive way of seeing it is Alice is taking 2 bits, encoding it in 6 bits, so the rate is 2 over 6, or 1/3. So with this definition, it's easy to see that larger rate is better, because larger rate corresponds to a longer message, so you're blowing up the message less. To encode it, you need less redundancy or overhead. Okay, so if all we want is codes of large rate, then we just take C to be the set of all binary strings, so obviously we want something else, and that something else is error tolerance. So we have some notion of error tolerance P, and what exactly it means to have error tolerance P depends very much on the model of the errors being applied. What kind of errors, and are they adversarial, are they random? In this talk, we'll be dealing with deletion errors. So traditional coding theory studies substitutions and erasures. Substitutions are bit flips, and erasures are you replace a bit with a question mark. Deletions are like erasures, but you don't know the positions of the deleted bits, so you get a strictly shorter string, a subsequence of the transmitted string. And we'll be dealing with worst case deletion. So you imagine there's an adversary sitting in between Alice and Bob with a budget of deletions and applies them in the worst possible way. So now that we've specified the error model, we can define exactly what it means to have error tolerance P. We use this definition. A code corrects Pn worst case deletions if and only if the LCS of the set is less than n minus P times n. So why does this correspond to the protocol? This definition says that for any two strings Alice sends, they can never map to the same output on Bob's end. So for anything Bob receives, he can always figure out which message, there's at most one code word it could have come from, so Bob, at least combinatorially, can always figure out the correct message. So if you think about this for a minute, you'll convince yourself this is the right definition, but the point is it's a purely mathematical definition. So now we want codes with large rate. We also want to tolerate more errors, and so the natural question is, what's the optimal R versus P trade-off? And this is a question that appears all over coding theory for pretty much any error model, and we're studying it here for worst case deletion. So it's this basic question for a basic model. So this trade-off is in fact open. It was originally studied by Ullman in the 60s. And in fact, not only is the trade-off open, but our knowledge is actually quite embarrassing. So we do not even know what is P threshold, which is the supremum of P for which R is bigger than 0. So what do I mean by R is bigger than 0? I mean we can find positive rate codes that correct P, have error tolerance P. And by positive rate, I mean asymptotically positive, where the size of the code is exponential in n. So this trade-off is asking for, what's the curve of R versus P values that are achievable with a code, and this open and embarrassing question is just asking for what is the p-intercept of this curve, and this in fact is still open. By contrast, this threshold has been known for erasures and substitutions since the 50s, but for deletions it's still open. And in fact, for deletions it's even more embarrassing. We don't even know if the threshold can approach 1/2. So 1/2 is a natural bound for the threshold because it's the adversary can always delete all the zeros or all the ones. So you can't correct a half fraction of deletions, but could you correct, a half minus epsilon for any epsilon? And it was not known until our work, where we showed that no, the threshold cannot be a half, that it's bounded away from a half. So previously, what was known about the threshold? There was a trivial upper bound, as I mentioned, of 1/2, that you can't correct n over 2 worst case deletions, and this follows from the warm-up question on the first slide, that in any set of binary strings, at least 3 binary strings, there's 2 with LCS n over 2. In terms of constructions, there's been a bunch of constructions given, the best one showing that the threshold is at least 0.41. So combinatorially, the result is there exists a set of exponentially many binary strings such that the LCS between any two is at most 0.59. This is the best lower bound, and as I mentioned, our result proves that the threshold is strictly less than a half, so bounded away from half, improving on the trivial bound. One last result I'll mention in the same direction as our result is the following, that shows that in any set of log n many binary strings, there's 2 with LCS, not n over 2 plus delta n, but n over 2 plus n over some polylog. So it's in the same direction, but doesn't quite get a bound on the threshold. So just to summarize our result, we prove this combinatorics result, that among any set of quasi-polynomially many binary strings, there are 2 with LCS n over 2 plus some delta n. It's a combinatorics result. It's also a basic coding theory result about what's the threshold of adversarial deletions. And another reason you might care about this is, if you look at our result, it's purely a question of finding long common subsequences, and common subsequences appear all over computer science. So could you apply some of the new techniques we developed to other problems? Now I'll tell you about the main ideas in our result. The first idea is pigeonholing by statistics. So notice that in our result, we need to choose 2 things. We need to choose two code words or 2 strings, and then we need to choose a common subsequence that's large. So the pigeonholing chooses the 2 code words. So for every code word, we measure some statistics. So we count the number of zeros, we count the number of zeros in the first half, and some other things that are too technical to define. And we're going to do this such that the total number of possible statistics is at most quasi-polynomial. So then if the number of code words is more than the number of possible statistics, then by pigeonhole there are 2 code words with the same statistics. So they have the same number of zeros, same number of ones, and all these other things are the same. And that's and that's all we do to choose the 2 code words. And this is the only place in the proof where we use the size of our code. So once we have the 2 code words, then we need to find a long common subsequence, and we do this with one of 3 matching strategies. So you can think of finding a long common subsequence as sort of you're doing some kind of matching between the bits of one string and you're trying to find a large matching. And we have three ways of doing this. And very roughly, all these three matching strategies function the same way. Because the strings have the same number of zeros and ones, then you first find a matching that, say, matches all the ones. This has length at least n over 2, and then you find judicious points to switch from matching ones to matching zeros, where it's sort of regions of the strings that are zero rich. So we give three different ways to do it, and we prove this structure lemma that says that at every point in the string, one of these strategies is always going to work. It's always going to give you a constant fraction advantage in the LCS. And very roughly, you should think of the structure lemma as proving some kind of Fourier transform. So it kind of classifies strings by how frequently they're oscillating between zeros and ones. So then in the pigeonhole, we store these oscillation information, and then these matching strategies work by saying if you have two strings that are oscillating at roughly the same period, then you're going to be able to find nice places to switch from matching ones to matching zeros. That's very roughly the idea. So lastly, to make one of the matching strategies work, we prove a string regularity lemma. So Semiretti's regularity lemma is a powerful tool in additive combinatorics and graph theory, and we prove an adaptation of this graph regularity lemma to strings. And previously such string regularity lemmas were known, but we need to prove a different version of it for our application. So to illustrate some of these ideas, I'm going to prove an easier version of a result where we don't get an advantage of delta n, but an advantage of n over log squared n, and it's going to simplify the proof a bit, and I'll be able to explain the ideas. And notice this simpler result, this easier result, still is an improvement over the previously best bound of Buchan-Mott that gets an advantage of n over log to the 10. So this weaker result, you only need two matching strategies, the imbalance strategy and the green strategy. The imbalance strategy just matches all the ones or all the zeros. So because we do this pigeonhole to select our two strings, they have the same number of zeros and ones, and so if you match all the ones, and let's say both strings have at least n over 2 plus some delta n ones, then you've already found a long common subsequence and you're done. Similarly, if you have at least that many zeros, you're also done. So we may assume that our string is roughly balanced, roughly has n over 2 ones. Okay, so if the imbalance strategy doesn't work, we may assume our strings are balanced, and then we apply the green strategy. So the green strategy uses the following technical definition. A green L flag is an index I such that at least 1 plus epsilon times L minus 1 zeros appear between the ith and I plus L 1. Here think of epsilon as something like 0.1. And so it's easiest to see this with an example. Here S is some string, and I claim that 2 and 11 are green 4 flags in S. So between the second, 2 is a green 4 flag because between the second one, which is highlighted green, and the sixth one, but the lightly highlighted green region has more zeros than ones, and so 2 is a green 4 flag. Similarly, between the 11th one and the 11 plus 4 or 15th one in S, there's more zeros than ones, so 11 is a green 4 flag. Okay, so that's what it means to be a flag, and here's another string T, and you can check that in the string T, 2 is also a green 4 flag in T, and 11 is also a green 4 flag in T. So now with the setup, we can find a nice common subsequence between S and T by matching all the ones in S with all the ones in T, and every time we hit these indices that are green flags in both S and T, we switch to matching zeros. So here we match ones, but in between, say, the second and the sixth one, we match zeros, and between the 11th and the 15th one, we also match zeros. So this uses the flags, and because these are green flags, then we get a constant fraction advantage each time we do this matching. So now suppose we have two strings S and T that each have lots of green L flags. So S has some set of Gn indices that are all green L flags. T has some set of indices that are all green L flags. If these indices are randomly distributed, they're not, but if they were, then in expectation, roughly G squared n of the indices would overlap. So the set of green L flags would have at least G squared n common elements. So This is hand waving, but you can formalize it with a random shifting argument, which we'll sweep under the rug. So for now, let's just pretend that this means S and T have G squared and common green L flags, just like these two strings have 2 and 11 as common green 4 flags. Then I claim this means that S and T has a common subsequence with a significant advantage over n over 2. And this is because, well, you just do the green strategy. You match the ones, and every time you find a common green L flag, then you switch to matching zeros for the next L1s, and then you go back to matching ones. And so every time you do this switch, you use a flag, you gain epsilon L bits in your matching or in your common subsequence. And how many times do you get to do this switch? There's G squared n flags to use, but every time you use a flag, you potentially skip over L other flags. So you get to use this at least G squared n over L times. Each time you get an advantage of epsilon L, so the total advantage is epsilon G squared n over the trivial n over 2 matching. So this gives you a long common subsequence if you have such an S and T. And what we show in this structure lemma is that in every balanced string, there always exists some L such that G of L is at least 1 over log n. So there's always some L such that the string has at least n over log n green L flags. There's a bit of a caveat. It's either the string or the reverse string, but we sweep that under the rug for now too. So just pretend it's this. And the intuition is that most of the indices are L flags for some L of power of 2. This is not quite a true statement, but that's roughly the way you want to think about this, that we only need to consider L of power of 2. There's log n of them. Most indices are an L flag for some L, so that means by pigeonhole, there's some L where there's at least n over log n green L flags. So now, once we've proven this structure lemma, then we just include with our pigeonholing not just the number of ones and the number of zeros, but also the L such that you have a lot of green L flags. And then in your set of binary strings, to prove the final result, you find two strings with the same number of zeros and ones, and also the same L such that they have lots of green L flags. So S and T such that they each have n over log n green L flags for the same L, and then that implies that their LCS is at least n over 2 plus n over log squared n by this hand-wavy argument. Okay, so I swept under the rug something about reversing the string and something about this random shifting argument, but if you add in all that machinery, this idea works. So this is great. This proves that you can get LCS n over 2 plus n over log squared n. But if we're just using the imbalance strategy and the green strategy, this is the best we can do. So for this baby structure lemma that we proved that G of L is at least 1 over log n for some L, and there's some counterexample that I've shown here that shows that this is tight. So that means the imbalance and green strategies together cannot give you some LCS with a constant fraction advantage over n over 2. So this means for the full result, we need an additional strategy, and that strategy is the blue-yellow strategy, and you can read our paper to learn more. So in light of our work, there's a number of interesting open questions, the most obvious being, what is this p threshold? It's at least square root 2 minus 1. We know our work shows it's less than a half, but there's still a gap to close. And also, what's the right bound on the size of C? So we think that even if you have logarithmically many strings, that there should be 2 with LCS n over 2 plus delta n. So can you improve our quasi-polynomial bounds? And can you also extend this to list decodings, proving limitations for list decoding with list size 2 against worst case deletions? In general, can you prove better rate versus error fraction trade-offs for worst case deletions? Not just for this 0 rate threshold, but for larger rates as well. And can you apply these techniques that we used for finding common subsequences to other subsequence problems? So that's all. Thanks for your time.